All right, this is part 2, starting at number 71. So, how many grams of N2 are required to react with 100 grams of H2, according to this equation? So, a little bit of classic stoichiometry. So, it gives us N2 plus H2 yields NH3. Very common equation in chemistry. So, there's a 2 there and a 3 there, giving us a 1 to 3 to 2 ratio. This is called the Haber process. It's a way that nitrogen was fixed from the air to turn into a usable product. They use this to make fertilizer. They also use it to make explosives. So it's kind of the best of both worlds. Anyway, the problem says we have 100 grams of H2. So 100 grams of H2. Let's turn that into moles. So 1 mole. Hydrogen is 1.01. So H2 is going to be 2.02 grams. This will be around 50. Well, let's see. 100 over 2.02, 49.5. And that's moles of H2. Okay, so this is going to go here. Okay, so that's how many moles of H2. Question's saying, 71. Question's saying, how many grams of N2 are required? So here's my X. Right? So it's a 3 to 1 mole ratio. So I'm going to say 49.5 divided by 3 gives me 16.5. 16.5 moles of N2. And the question is asking for grams, so we just need to convert this into grams. So N2 is 28.02 grams per mole. 3 sig figs, 462 grams of N2. Okay, just make sure. Yep. All right, 72. What volume of NH3 gas at STP could be produced from the same thing? Okay, so excess nitrogen gas. So let's go back here. So with the same amount of hydrogen, how many liters or how much volume of this could we make? So this time we're going to solve for this one. So it's a 3 to 2 mole ratio. So I'm going to divide that by 1.5. You can also cross multiply. This times 2 equals 3 times x. So 49.5 times divided by 1.5 is going to be 33. So going to be 33.0. And that's moles of NH3. Now the problem says it's at STP. So we can use that STP shortcut where 1 mole equals 22.4 liters. So if I just multiply my 33 moles by 22.4 liters per mole, I'll get my answer here. And with 3 sig figs, 739 liters. Okay? The other way to do this would be to use the ideal gas law. STP tells you 2 things. It tells you the temperature and it tells you the pressure. So here's your moles. Your pressure is standard pressure. Your temperature is standard pressure. The R value is always known. You're going to rearrange and solve for V, and you should end up with that exact same answer. All right, 73. How many moles of NH3 could be produced from the above reaction? Okay, so it's the same thing, but now it's going to be a limiting reactant problem. So let me rewrite the equation. So we have nitrogen plus 3 hydrogens yields 2 NH3, which is ammonia. So we're going to have 120 grams of nitrogen, and we're going to have 21.0 grams of hydrogen. So we need to turn both of these into moles. So times 1 mole over 28.02. For hydrogen, it's times 1 mole over 2.01. 120 over 28.02 gives me 4.28 moles of N2, and 21 over 2.01, or 2. 21 over 2.02 gives me 10.4 moles of H2. So we have a 1 to 3 to 2 mole ratio, and I have 4.28 moles of this, and I have 10.4 moles of this. Anytime you're given the amounts of both of your reactants, you can't just pick your favorite one. You have to find out which is the limiting and solve based on that one. So the way I would do this is I would say it's a 1-to-3 ratio. So if I have this many moles of N2, I'm going to need 3 times as much over here. Now I can do this in my head. 4.28 times 3, that's going to be at least 12, right? Because 4 times 3 would be 12. So I'm going to need more than 12. I already can tell I don't have enough. I only have 10.4. I don't have enough of this, which means my limiting reactant is the hydrogen. And now that we have the limiting reactant, this is the one we're going to use. Because if we use that, it would be a nice easy 1-to-2 ratio. You would get the wrong answer because you don't have enough of this. Okay, so 3-to-2 mole ratio, I'm going to divide this by 1.5, or you can cross multiply. So I got 6.93 moles of NH3. I believe that's what it asks for. Yeah. Okay. 74. Okay. What type of intermolecular forces are present in these molecules? Okay, so this will take a little bit of work here. So in order to find out which intermolecular forces are at play, you need to find out whether it's covalent, whether it's polar or nonpolar. And the way you do that is by looking at the molecular geometry. So CO2, let's see. We're going to put the carbon in the middle and the 2 oxygens. I'm making a Lewis structure first. That's what we have to do here. Okay, we put dots around all of these. There are no hydrogens, so everything's going to get dots. All right. Now, this might be correct. It might not be. Carbon is 4. 2 oxygens is 12, giving us 16. If we have 16 here, then we're good. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 4 too many. What that means is I'm going to have to combine to 2 different times. If you make one double bond, that's going to cut 2 electrons out. If you make another double bond, that's going to cut 4 out. Now, you could technically do a triple bond and a single bond, but in that case, it's not very balanced. So what we're going to do is 2 double bonds. So I'm going to remove 2 electrons from adjacent, pairs of electrons from adjacent atoms and make a double bond. And then over here, I'm going to remove 2 electrons from both and make another bond. And if we kind of rearrange these, the dots would really be like here and here, here and here. And let's just confirm. 2, 4, 6, 8, 10, 12, 14, 16. So this is the correct Lewis structure. Now for Vesper, look at the central atom and think how many regions of bonding or electrons do we have? Well, I have a double bond here and a double bond here. Each of those count as just one region. Remember, a single, double, or triple bond, or a lone pair all mean the same thing when it comes to geometry. So this is basically a carbon in the middle with one thing coming out one side and one thing coming out the other side. These 2 markers are, of course, repelled from one another, so they're going to go as far apart as possible. So your CO2 is going to be linear. It's not going to be like a water molecule. These would never naturally bend down like this because there's no lone pair forcing them to do that. So because this is linear, it's going to be nonpolar. So linear and therefore nonpolar. So the question was IMFs. If it's nonpolar, there's only one type of IMF it could possibly have, the weakest of the weak, London dispersion forces. In order to have anything else, you need to at least be polar. So this only has LDFs, which explains why CO2 has a pathetically small boiling point. It's not even really a boiling point, it sublimes at -86 Celsius. Okay, several more of these, so we'll go hopefully a little quicker. H2O. So central O, H, with dots there. All right, H2O has 2 valence electrons in the H's, 6 in the O, total of 8. 2, 4, 6, 8. So this is in fact the correct one. Now what's the geometry of this? At first glance you might say linear, because look, it goes straight across, but that's not right. You're not thinking 3-dimensionally. There are 4 electron regions coming off that O. So if I had 4 markers in my hand, and these markers all hate one another, they're not going to naturally arrange themselves in a cross pattern. It's not going to be like this. You're thinking 2-dimensionally. They're really going to arrange themselves in this tetrahedral shape where it'll sort of look, I don't know how well that's coming off on camera there, but it's going to look sort of something like, that last one go. Or something, okay, that's not working with the camera. But it's going to basically arrange itself in this tetrahedral shape where we have kind of like a triangular base with one coming off the top. So anyway, The two lone pairs don't actually appear, so if we take two of these away, that's our shape of water. We have a bent structure. So bent, and therefore polar. Okay? And because it's polar, it's not just going to have London dispersion forces, so we'll list it. It will have LDFs, but it'll also have dipole-dipole forces. Okay? Because it's polar. Now, the question is hydrogen bonds. Does this have hydrogen bonds? Yes, of course it does. You all know water has hydrogen bonds, and it's because it's O bonded to H. So this is going to have hydrogen bonds. So this water has all three trophies, as I use in my metaphor. It has, you know, the participation trophy, the division trophy, and the championship trophy. And that's why water, for such a teeny tiny molecule, has an impressively high boiling point. All right, the next one is xenon, Xe. Xenon's a noble gas. Nothing bonds to it. It's just an atom. Atoms can never be polar. You know, it could have slight differences, like those London dispersion forces create slight temporary dipoles, but this can't be polar, so it can only possibly have LDFs. That's it. And that's why noble gases have very low boiling points. Okay. The next one is PCl3, phosphorus trichloride, PCl3. Okay, so phosphorus goes in the middle. The three chlorines will arrange like this. We need a lone pair here, and then we need pairs for all of these chlorines. Okay, let's see if this is correct. So phosphorus is 5, chlorine is 7, times 3 is 21, for a total of 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So this is, in fact, correct. Now, if you picture this three-dimensionally, what structure is this going to have? Well, you have 4 bonding regions around that central phosphorus. So when you have 4 regions, it's not going to make a cross shape. It's going to make a tetrahedral shape. So you're going to have the phosphorus in the middle, and you're going to have like these 3, generally show it like that, like 3 legs like a tripod. Okay, so it's like this one's in the back behind the board. So it's like a tripod with a phosphorus there. And then here's your lone pair sitting on the top, like this. But in reality, you don't really see that there. So this is all you really see. Now, what shape is this? Is that trigonal planar? No. If it were a triangle on a flat plane, then yes, it would be, but this is not. It's bent down like that. So it's not called bent, it's called trigonal pyramidal or pyramidal. So trigonal pyramidal. And because of that lone pair there, that's what gives it this asymmetry. That's going to be polar. So which IMFs does this have? Does it have London dispersion forces? Of course it does. All molecules do. So it's going to have LDFs. It's polar. So therefore, yes, it has dipole-dipole. I'll say di-di. And does it have hydrogen bonds? No. So this is going to have somewhat high boiling point because at least it's polar, but no hydrogen bonds here. All right, I think there's one more in this problem. This is a long problem. CH4. Okay, CH4. So central carbon, 4 H's. All right, hydrogen does not get lone pairs because it's done with 2. And this is complete. Let's check. So carbon is 4, plus 4 hydrogens is 8. 2, 4, 6, 8. So this is correct. Okay? So we've been over this a few times. When you have 4 bonding regions, 4 electron regions coming off the center, it's going to be a tetrahedral shape. So this is going to look like 1, 2, 3, 4. Not my best tetrahedral, but you can see that it's going to be perfectly balanced like this. So even though the CH bond has a little bit of polarity to it, it's a symmetrical shape, tetrahedral, which makes it nonpolar. Nonpolar. So if it's nonpolar, which IMFs does it have? Well, it only has the weakest of the weak, London dispersion forces. So LDF only. No dipole-dipole. And even though we have C and H, that doesn't count as a hydrogen bond. A hydrogen bond requires it to be H bonded either N, O, or F. This is not a hydrogen bond, and that's why this is going to have a pathetically low boiling point. I think this is like -190 90 something, or I think it's actually lower. You can Google it, I'm sure. Methane boiling point is probably like around negative 240 something. Very small molecule. Okay, 75. These should go quicker now. So NH3, NF3. The question says, why does this have a lower boiling point than this? Now the reason that's an interesting question is because this NF3 is much, much heavier than this. The molar mass of this is going to be about 17 because this is 14 and 3. Let's see, 3 fluorines, each fluorine is 19, so 19 times 3 plus 14, this is going to be 71. Okay, so that's the molar mass, grams per mole. So this is much heavier, and generally, the heavier the molecule, the higher the boiling point because of the stronger London dispersion forces. But there's something else at play here, and hopefully you recognize it. This has hydrogen bonds because it's N bonded to H. It's going to be one N in the middle with 3 H's sticking off of it. So because of the hydrogen bonds, this is going to have a much higher boiling point and melting point. It's that strongest of the strong intermolecular forces. Okay? Now these are both going to be polar. If you do the Lewis structure, you're going to end up seeing that they're both trigonal pyramidal, where the N has a lone pair sticking off the top, which skews those 3 legs down. So they're both going to have dipole-dipole. They're of course both going to have London dispersion forces, but only this has hydrogen bonds, which is why it's going to have the higher boiling point. 76. Why does argon have a higher boiling point than helium? No, neon. Okay, so argon, atomic number 18, molar mass of 39.95. Neon, molar mass of 20.17. So you can see that the argon is about twice as heavy as the neon. These are both noble gases. They can't possibly have any polarity to them, so they only have London dispersion forces. And because neon is smaller, it's going to have weaker London dispersion forces than argon, and that's why it's going to have the lower boiling point. The reason for this is neon's going to have 10 protons and 10 electrons that can shift from one side to the other to create that temporary dipole. Argon is going to have 18 protons, 18 electrons, which can shift. So because there are more protons and electrons temporarily shifting, that's going to create that stronger London dispersion force here compared to here. 77. All right, so we're categorizing bonds. So let me write these all out. So we have CH, NO, MgS, ClCl, and HF. All right. So you need a chart that lists electronegativities. You will likely get something like this on your final, but check with your teacher. And you will also likely get this electronegativity range, but again, check with your teacher. So basically, we're going to look up the difference in electronegativity between the two elements and see where it falls. All right, so I can do this the quickest by just listing them all right now. So hydrogen is going to be 2.1, carbon is 2.5, oxygen is 3.5, nitrogen is 3.0, I believe. Yep. Sulfur, 2.5, magnesium 1.2, chlorine is 3.0, chlorine is 3.0, fluorine, you all know that, 4.0. It's the highest electronegativity, hydrogen is 2.1. So I can already tell that we're going to see that the range that you see here, right there, it's sort of like a guideline. You'll see what I mean in a second. So the difference here, the change in electronegativity is 0.4. According to this, is going to be a polar covalent bond. So there's a little bit of polarity, and those electrons are pulled towards the one with the higher electronegativity. So these two shared electrons are going to end up a little bit closer to the carbon than the hydrogen. Think of hydrogen as like the weakest of the nonmetals. It's, you know, it's the kid on the playground that gets bullied by all these other nonmetals. So the electrons are getting pulled away from it. Here, the oxygen is a little bit stronger than the nitrogen difference is 0.5. So this is also going to be very slightly polar covalent. So we have polar covalent, but again, just slightly. Here we have a difference of 2.5, and that is going to fall, yes, that'll fall in our ionic range. Okay, and you should have known that. Magnesium and, oh wait a minute, no, I'm looking at 2.5. The difference here is subtract that, it's going to be 1.3. Now, according to this, that's going to fall in the polar covalent range, but this, we've talked about, this is more ionic than it is covalent. So you can see that this doesn't necessarily hold true 100%. So we consider this to be ionic, but technically, if we're being consistent with our chart, this will also be polar covalent. 3.0, 3.0, there is no difference there. So that's going to give us a nonpolar covalent. In fact, we can even call this a perfectly nonpolar covalent bond. This would be like a chlorine gas molecule. And then finally, HF. The difference here is 1.9. According to this, that's ionic. Now, HF is not really going to be ionic because it's two nonmetals, but you can see it's so impressively different that it's almost as if it's ionic. It's strong enough, the difference is big enough to almost be pretty much ionic. And this expresses that hydrogen bond. H and F is going to have a huge difference in electronegativity. So these electrons are going to be held extremely close to the fluorine. Like, it's on the verge of stealing it, but the hydrogen's just barely holding on. So that hydrogen is going to be very much partially positive. The fluorine's going to be very much partially negative, and that's going to be that hydrogen bond there. All right, 78. Two solutions are mixed, and we're looking for total and net ionic equations and spectator ions. So I'll start with the standard balanced equation. So we have silver nitrate, and because I told you it's a solution, it's going to be aqueous, and that's going to bond with sodium chloride. All right, so double replacement. The silver goes with the chloride, AgCl. Don't forget, silver is part of that 3-2-1 rule on the periodic table. It's going to have a charge of plus. Even though it's in the middle of the transition metals, it's consistent. It's a type 1 metal. It always has a charge of just plus. You check your solubility table. This ends up being solid. The other product is NaNO3. You check your table, that's going to be aqueous. Now this happens to be balanced already, should make it a little easier. So the total ionic equation, we showed this earlier. You basically split the aqueuses up and you keep the solid together. So I'll try to squeeze this all on the same line. Ag plus aqueous plus NO3 minus aqueous. Remember, polyatomics stick together as a team. Plus Na plus aqueous plus Cl minus aqueous yields, this is going to stay together, plus Na plus aqueous plus NO3 minus aqueous. All right. So you can see this is a better way of representing what really happens. We didn't really have sodium nitrate, silver nitrate. We didn't really have sodium chloride because these would naturally be solid ionic compounds. We really had water with these ions randomly floating around, water with these ions randomly floating around. And that's what is shown here. We took silver ions, nitrate ions, sodium ions, chloride ions. We threw them together. We ended up getting a product, silver chloride, and then you had leftover sodium and leftover nitrate ions. So the net ionic equation, I'll do in green, it's only the components that actually did something. The silver bonded with the chloride to form solid silver chloride. Let me restart this, hold on. Save as come on. Alright, well, okay, let's try this from brand new. Fortunately, I don't have too much more to do. Alright, so that was question 79. Check. That was 78. Okay, so again, in the spectator ions, I didn't get to that. The spectator ions were just the ones that didn't do anything, so that would be the sodium and the nitrate. Alright, this is 79. 79 says convert 63 liters into cubic meters. So we're going to go from liters, and we're eventually going to get to meters cubed. So we have a volume unit going to a volume unit, but notice this is like a liquid volume, and that's a cubic volume. What's that bridge that we use to cross over? You remember way back we learned that 1 milliliter equals 1 centimeter cubed. So what we're going to do here is go from liters to milliliters to centimeters cubed to meters cubed. Okay. 63 liters times 1,000 milliliters per liter times, now it's a 1-to-1 ratio, 1 centimeter cubed per 1 milliliter. All right, so that gets us into centimeters cubed. Now to go into meters cubed, you cannot do this. Let me show you what you cannot do. 1 meter cubed over 100 centimeters cubed, because that is not correct. What you have to do is say 1 meter over 100 centimeters cubed on the outside. Or I usually just do it this way. Repeat it 3 times. 1 meter over 100 centimeters. Okay? If we check our units, centimeter cubed cancels centimeter, centimeter, centimeter. We're left with meter times meter times meter, which is meter cubed. We do the math on this. 63 times 1,000 divided by 100 cubed, 0.063 meters cubed. Okay. Number 80. What volume of carbon dioxide gas is released by the complete combustion of 59 grams of methane? Assume 312 degrees and it's at standard pressure. Okay. So we start with a balanced equation. So methane is CH4, and we're going to react that with oxygen gas. Methane is naturally a gas. And we're going to form CO2 gas plus H2O. And we can assume that's a gas as well. So I always say H, then C, then O. I think of these as like hardcore balancing. So HCO is the order of letters in that word. So H is, I have 4 here and 2 there. So let me try a 2. And that's going to be fine. I consider odds and evens here. The 2 is going to make the O even, which is good. So H's are good. Carbon, 1 and 1. Okay. Oxygen. I have 2 here and 2 here. That's 4. I need a 2 there. So balancing method is pretty easy. 1, 2, 1, 2. All right, so the problem says we have 59 grams of methane. We're looking for the CO2 produced. So let's take our 59 grams of methane, CH4, and we're going to multiply that times 1 mole over the molar mass of methane, which is going to be 16.04, or something very close to that. 16.04 is pretty close. 59 over 16.04 gives us 3.68 moles of CH4. 3.68 moles. So the question is asking about CO2. Notice it's a nice easy 1-to-1 ratio. So the moles of CH4 are going to also equal the moles of CO2. Nice and easy. Okay, but the question doesn't ask for moles, it asks for what volume, and it's not an STP, so we can't use that shortcut, the 22.4. So we're going to have to use the ideal gas law. So PV equals nRT. We're looking for volume, so that's equals to nRT over P. We have to convert all of our units to make sure they're correct, because when you use this, you have to use liters, you have to use ATM, and you have to use Kelvin. So question 80, okay, so the temperature is 312. We're going to add 273 to that, giving us 585 Kelvin. Standard pressure, it says. Now, we could choose whatever unit we want for standard pressure. It could be 1 ATM, it could be 760 mmHg, 760 torr. Obviously, we're going to choose 1 ATM because that's what we have to use. So, volume equals N is 3.68 moles. R is 0.0821 liters atmospheres over mole Kelvin. T is 585 Kelvin. And P is 1 ATM. and that's an infinite one, 1.0000. Mole cancels mole, Kelvin cancels Kelvin, ATM, ATM. We're left with liters, which makes sense. Let's see what we get. 3.86 times 0.0821 times 585 divided by 1 with 3 sig figs. Question 80. 2 sig figs, 180. And the unit is liters. Okay. 81. We have 83 grams of water. It's at 22 degrees and it's going to completely freeze. We're saying how much heat is required. So, heating curve, up, flat, up, flat, up. We're starting at 22 degrees. That's going to be about here. And we're going to cool it down, not until it reaches freezing point, but until it totally freezes, which is going to be here. So we're going this way, and it's going to be a two-step process. So the first thing that's going to happen is it's going to cool down from 22 to 0. So we're going to use Q equals mc2 delta T. And we're going to plug in, let's see, our mass is 80.3. The value of C2 is going to be 4.18 joules per gram degree Celsius, joules. And our change in temperature, we're going from 22 to 0, so we're going to say 22. Your teacher might prefer you use negative 22 and end up with negative joules here. I usually just use absolute value. It's a change of 22 degrees, whether it's positive or negative. Let's see what we get. 80.3 times 4.18 times 22, 7,384 joules. I'll deal with sig figs after. Now, we're not done because it now has to freeze. So this equation here is going to be Q equals mass times the latent heat of fusion, which is going to be 80.3 grams times 334 joules per gram. 80.3 times 334, 26,820 joules. So we're going to add these two together. And let's check our sig figs. Looks like it's going to be a 2 sig figs because of the 22 degrees. So 34,000. So that's how much heat must have been released in order for it to cool down. All right, 82. Why does sugar, C12H22O11, that's technically sucrose, why does that melt at 160? While salt, NaCl, melts at 800. So this all comes down to the structure. So sugar is C12H22O11. Non-metal, non-metal, non-metal. This is going to be covalently bonded. So we can represent sugar molecules as like a big molecule like this. I mean, technically you could do like, 12 circles for C's, 22 circles for H's, and 11 circles for O's. We'll just call that a sugar molecule. Now, when you have a sample of sugar, you have a bunch of these sugar molecules hanging out near one another, but they're not actually bonded. They're only held together by what? IMFs. These represent IMFs. Okay, these are not ionic or covalent bonds. These are intermolecular forces. This is a molecule, sugar molecules, held together by those IMFs. Now, this is a very heavy molecule, so it's going to have impressively strong IMFs. That's why sugar's, at least it's a solid at room temperature. And this is also, if you look at the structure of sugar, which you're not expected to be able to map out, it is slightly polar, actually, I believe very polar, and it has hydrogen bonds. Some of these H's are bonded to some of these O's. So there are hydrogen bonds. So this has all 3 IMFs, but that still pales in comparison to ionic bonds. So these are held together by IMFs. Compare that to NaCl. Compare that to NaCl. When you have NaCl, you have Na plus and Cl minus ions. So it's like NaCl, NaCl. And this repeats in all these dimensions. Okay? It's not just this, it's 3-dimensional as well. It's this entire cubic structure over and over and over again of NaCl. And these are not IMFs connecting these. These are pure, strong ionic bonds. So because this is held by a network of ionic bonds, where every single one is held on all sides by one of the opposite charge, this gives it incredible strength. This is why an ionic compound like NaCl is going to melt at a much, much higher temperature than a covalent molecule like sugar. Last question. Empirical and molecular formula are actually just empirical. All right, so we have 9.8 grams of nitrogen. We have 0.70 grams of hydrogen, and we have 33.8 grams of oxygen. So it gave us grams, so we just turn those right into moles. If it gives you percentages, you assume they're grams, and then you turn it into moles. All right, so setting this up, nitrogen's molar mass is 14.01 grams. Hydrogen is 1.01 grams. And oxygen is 16.00 grams. Let's see what we get. 9.8 over 14.01 gives us 0.70 moles of nitrogen. 0.70 over 1.01 gives us 0.69 moles of hydrogen. And 33.8 divided by 16 gives us 2.1, or 2.11 moles of O. Okay, do you recognize the pattern? Actually, this time I do. I'm noticing 0.7, 0.7, and 2.1. I can tell that's a 1:1:3 ratio. If you can't tell, if you aren't sure, divide them all by the smallest number, which in this case is 0.69. And when you do that, this is going to be exactly 1. This is going to be incredibly close to 1, and that's going to be very close to 3. So you're going to see the 1:1:3 ratio, NH03. And now that we've been through a whole year of chemistry, you can probably recognize that this is actually HNO3, which, when it's aqueous, is nitric acid. So that's your empirical formula. All right, good luck.